everybody, I hope you guys are having a wonderful day. In this video, we're going to talk about the apportionment paradoxes, which are part of the reason why we decided to switch from Hamilton's method to Jefferson's method when apportioning representatives between the states. So take 3 deep breaths and let's make this math easy. All right, so I mentioned in the introduction that the apportionment paradoxes are part of the reason why we decided to switch from Hamilton's method to Jefferson's method. And these paradoxes actually showed up in real elections or real apportionment situations after some of the censuses, because we always apportion out the representatives to the states every 10 years based on the results of the population changes that are recorded in the census. So the first paradox is called the Alabama paradox because it happened after the reapportionment in the 1880 census. Because in this situation, they calculated all the populations, they figured out how many representatives there were supposed to be, and then Congress voted and decided to increase the total number of representatives because the country had grown enough that they felt like it would be good to have more representatives than the current amount they had. And when they redistributed those representatives where there were more representatives, Alabama actually lost a representative. So to see a simplified example of why this would happen, let's look at this situation where you have 3 people who are investing in a treasure dive, and they each invest a different amount, and the dive results in 35 gold coins. If we were to use Hamilton's method to distribute these coins to the investors based on their investment amount, we would first start by finding the total investment amount, which when we add up all of those numbers, it ends up being $14,000. And if you take that $14,000 and divide by the 35 gold coins, you get a standard divisor of 400. And if I take each one of these investment amounts and divide by that standard divisor of 400, because essentially it's saying that each gold coin should be equivalent to about $400 worth of investment money. And so we would say, okay, well, Christina invested $7,736. If I divide that by 400, I get the decimal 19.34. If I take Ermias's number and divide by 400, I get 12.31. And if I take Caden's number and divide by 400, I get 3.35. And the lower quotas for that would be 19, 12, and 3. But if I add up all of those numbers together, 19 plus 12 is 31, plus 3 is 34, which means we have one more gold coin that hasn't been apportioned yet. And so because Caden's decimal is the largest decimal, then that means that we'll give that extra gold coin to Caden, and he would get 4 of the gold coins that they found. So this would be kind of like what happened with the states before they decided to adjust the number of representatives. Now, let's say that instead of finding 35 gold coins, they actually found 36 coins. So in this situation, this is kind of like adding more representatives to be apportioned, like what happened in the 1880 census. So we would go through and we would recalculate this. And the total amount of money that was invested is still $14,000. However, when you divide 14,000 by 36 instead of 35, you get a standard divisor of, let's see, that's 388.88, which basically means that each gold coin is now equivalent to about $388 of investment money. And when I divide each of the investment amounts by 388, I get 19.89, 12.66, and 3.4. And if we look at the lower quotas, we would have 19 and 12 and 3. But if I add all of those up, 19 plus 12 is 31, plus 3 is 34. And because I have 36 coins to distribute, that means that I need to give the 2 extra coins to the people based on their decimal numbers. So this is the largest decimal, so I'll give Christina 20 coins. And then this is the next largest decimal, so I'll give Ermias 13 coins. And so this situation illustrates the Alabama paradox, because if you look at it, Caden started off with getting 4 gold coins, but then after they found another coin, he actually ended up with less coins, which is kind of a weird paradox that sometimes happens with Hamilton's method. And so obviously the people in Alabama were not very happy about this because they lost a representative, and that was one of the things that contributed to deciding to switch the method to Jefferson's method. Another paradox that happened with Hamilton's method was when Oklahoma became a state in 1907. So they had all of the representatives apportioned out to all of the states, and then Oklahoma became a new state, and Oklahoma's population required 5 representatives. And so it would make sense that because this new state was added, that some of the states, specifically 5 of them, would lose a representative to give the representatives to Oklahoma. But what actually happened was that 6 states lost a representative and Maine gained a representative, which was another odd paradox that happened that made people want to switch to using Jefferson's method instead of Hamilton's method. So to look at a simplified example of how this can happen, let's look at a situation where you have a school district that has 2 high schools, and the district could only afford to hire 14 guidance counselors. If we want to determine how many counselors should be assigned to each school with Hamilton's method, then first of all, let's look at what the total number of students are. So if we add up the number of enrollments, it looks like our total number of students is going to be 16,812. And if I do 16,812 divided by 14, that gives me my standard divisor of 1,200. So essentially, each counselor should be responsible for about 1,200 students. So if I take the number of students enrolled in Lowell School and divide that by 1,200, that ends up giving me the decimal 10.5224. If I take the number of students enrolled in Fairview and divide by 1,200, that gives me 3.4775. And so if I look at the lower quotas, I would have 10 counselors at Lowell and 3 at Fairview. But because I have 14 counselors and 10 plus 3 is 13, I have 1 additional leftover counselor to assign. And since this is the larger decimal, I'll assign it to Lowell. And so we would have 11 counselors at Lowell and 3 at Fairview. So now let's say that there are 512 students enrolled in a new school. And they would need to hire some more guidance counselors, obviously, so that the current ones are not overwhelmed. And if you calculate out 1,200 students per counselor for 512 students, that means that you would need to hire 4 new counselors. So now we have a total of 18 counselors total, because you have the 14 and the 4 that we added here. And if we calculate this out and we add up the total number of enrollments to distribute these 18 counselors, the total number of enrollments would be 21,924. And when you divide that number by 18, you get a standard divisor of 1218, which basically means each counselor is responsible for 1,218 students. So our standard divisor is now 1218. And if we divide each of the enrollments at each of the school by 1218, we end up with 10.37, 3.42, and 4.19. And so if we do the lower quotas, Lowell will get 10, Fairview will get 3, the new school will get 4, and this adds up to a total of 17 counselors, which means that I need to assign the one leftover counselor, because I have a total of 18, to one of the schools. And so since this decimal is the largest decimal, that means I would assign it to Fairview. And if you look at this, Lowell started off with 11 counselors, but now they only have 10. And that was a result of adding in the new school, which required some new counselors. And if you look at it, the 4 counselors that we hired to cover the new school are going to the new school. So it's not like Lowell lost a counselor to cover the new school. Lowell lost the counselor to Fairview because the decimals changed when you got a new standard divisor. And so that's a simplified example of what happened with the new states paradox. When it actually happened in real life, there were obviously a lot more states involved when Oklahoma became a state, so it was much more complicated to calculate. But that's kind of the general idea of what happens with the new states paradox. And then the last paradox that happened is the population paradox. So between the 1900 and 1910 censuses, Virginia's population, which was originally much bigger, grew 1.07% annually. And Maine's population, which is a smaller population, grew a smaller percentage. However, when the reapportionment happened between 1900 and 1910, Virginia actually lost a representative to Maine because of the way that the decimals worked out. So to see a simplified example of this, let's look at a state that has 5 different counties and 50 seats in each county. So if we were using Hamilton's method, we would have to add up the total of all of the populations, which in this case would be 1,440,000. And if you take that number and divide by 50, you get a standard divisor of 28,800. And that number, if you take each of the populations and divide by it, will give you the decimals 8.33, 4.33, 9.61, 11.33, and 16.38. And so with the lower quotas, we would have 8, 4, 9, 11, and 16 representatives for each county. If you add all of those up, that equals a total of 48 seats, which means that I have 2 leftover seats to assign. So I will assign it to this one first because that's the largest decimal. And then this one is the next largest decimal. So I'll scribble that one out and write 17. And so this would be the apportionment of the seats according to Hamilton's method. Now, let's say 10 years later, the populations are recounted and some of the populations changed. So this population grew by maybe about 13,000-ish. And this population also grew, but not as much. It only grew by about 1,000. If we calculate out the apportionment with Hamilton's method, then we would start by adding up this new population, which adds up to a total of 1,454,400. And if you take that number and divide by 50, the standard divisor would be 29,088. And so that would be our new standard divisor. And when we divide each of the populations by the standard divisor, we get 8.25, 4.29, 9.95, and 11.22, and 16.28. So the lower quotas would be 8, 4, 9, 11, and 16. And when we add all of those up, we get 48 seats, which means we have 2 leftovers again. And I'm going to give some of the leftovers to Madison County because that has the largest decimal. And then the next largest decimal is Clay County with 0.29. And so I would scribble this one out and give 5 representatives to that county. And if you look at this, essentially what happened is Clay County increased by 1 representative and Franklin County decreased by 1 representative, despite the fact that Clay County's population stayed the exact same, and Franklin's population grew a little bit. And again, this comes from the decimal relationship, where if you change the standard divisor, it may change the decimals enough to change the outcome of your apportionment. So these three paradoxes are situations that happened in real life, and they were part of the reason why we switched to Jefferson's method instead of using Hamilton's method. But Jefferson's method has its own issues because sometimes it will violate the quota rule. So remember, the quota is basically where you take the state's population and divide by the standard divisor. So let's say you had a state that had a quota of, I don't know, like 13.78 or something like that. This would be the quota of that state. And the quota rule says that the number of representatives that should be assigned to this state should either be 13 or 14. So essentially it should be within 1 unit of the quota, which is like the decimal number. But sometimes, depending on the size of the other populations of the other states you're working with, sometimes Jefferson's method might give you a result where this state might actually get 15 representatives, which means that it's more than one above the state's quota. And so that's one of the issues that comes up with Jefferson's method. So we actually don't use Hamilton's or Jefferson's method anymore. And that's one of your projects that you'll be doing. You'll look into what method we currently use to apportion representatives. But Hamilton's method definitely had a lot more issues than Jefferson's method did. And so people saw this as an improvement, and that's why we moved from Hamilton's method to Jefferson's method. So that's it for this lesson. If you have any questions, let me know.